Hello and welcome to our third lecture. Today we're going to finish chapter 2. We're going to be talking about autonomous equations and population dynamics, exact equations, and then finally using substitutions to change some difficult differential equations into easier differential equations. First of all, autonomous equations and population dynamics. What is an autonomous equation? An autonomous equation is an equation of the form dy dt is equal to f of y. We have a function here which is only a function of y. There's no functions of t in this equation. And I'm going to start with some examples about cats. Let's suppose that y of t is the number of cats in Istanbul. The simplest model that we could use is to assume that the rate of change of y is proportional to y. In other words, if there's lots of cats in Istanbul, then there'll be lots of baby cats and so on. So the number of cats in Istanbul will increase quickly. If there's not many cats in Istanbul, there'll be a small number of baby cats born. The number of cats in Istanbul will increase slowly. So the simplest model is just to assume that dy dt is equal to ry for some positive constant r. We know how to solve this initial value problem. This is just a separable equation. In fact, all autonomous equations are separable equations. The solution is just the initial condition y0, e to the power rt. And that looks like this. Now this is good for small y, that's not a problem there. But this model predicts that the number of cats in Istanbul increase exponentially for all time. This cannot be true. We can't have the number keep getting bigger and bigger and bigger and bigger. At some point the food will run out, or there'll be no space left for more cats, or the people will get angry with the cats, etc., etc. So we need a better model. Let's use a model with logistic growth. The idea here is we're going to replace our constant r with some function h of y. We want a function h which satisfies three properties. We want h of y to be approximately equal to r if y is small, because we were happy with the previous model when y was small. The problem with the previous model happened when y got bigger and bigger. So we want our function h of y to decrease as y grows larger. And in fact, we want h to become negative for large y. The simplest function h which satisfies these properties is h equal to r minus ay, which looks like this. If y is small, the function is approximately equal to r. As y increases, the function h decreases, and if y is big enough, h is a negative function. So we're going to be looking at the differential equation dy dt is equal to r minus ay y, or we could write this a slightly different way. We could write this as dy dt is equal to r 1 minus y over a constant k multiplied by y. This is called the logistic equation. First, we're going to look for equilibrium solutions to this equation. That is, we're going to be looking for solutions which have dy dt equal to 0 for all t. So we start with what we want. We want dy dt is equal to 0. And we see that this tells us we must have either y is 0 or y is k. These equilibrium solutions are important. If we look at some more solutions, and I'm going to show you some on a graph now, we can see that the other solutions either converge to y is equal to k, but they also diverge from y equal to 0. Here are some solutions to the logistic equation. The solutions are converging towards y is equal to k. They are diverging away from y is equal to 0. To understand this behavior, what we do is we graph dy dt against y. So here on the vertical axis, I have f of y, which is the same as dy dt. And on the horizontal axis, I have y. And then I'm plotting the function r, 1 minus y over k, y. As we said before, the equilibrium solutions, the points where dy dt is always equal to 0, are y equal to 0 and y is equal to k. Now, note that if dy dt is positive, that means y is increasing. If dy dt is negative, that means y is decreasing. We can show this on the graph by drawing some green arrows. Between 0 and k, dy dt is positive, y is increasing. We draw an arrow to the right to show that y is increasing or y is getting bigger. If y is bigger than k, then dy dt is a negative number, y is decreasing. To show that y is decreasing here, we draw an arrow to the left. To investigate further, we can look at the second derivative of y. Let's do this for the general equations, not just for the logistic equation. Let's look at dy dt is equal to f of y. Then d squared y dt squared is the derivative of f of y. That's f prime y dy dt by the chain rule, or f prime f. So we can say that the solution is concave up when both f and f prime are both positive or they're both negative. And we can say that the solution is concave down when one of f and f prime is positive and the other one is negative. Let's look again at this graph. Looking at the first part, between 0 and k over 2. Here, f is a positive function and f is increasing, so f prime is positive. Here, our solution y is increasing and concave up. Second part, between y over 2 and k. Again, the function f is a positive function here, but now f is decreasing, so f prime is negative. This tells us that our solution y must be increasing and concave down. And the third and final part of the graph, if y is bigger than k, y is a negative function, and f is a negative function, f is decreasing. So y must be decreasing, and because negative multiplied by negative is positive, it must be concave up. Moreover, if you remember the last theorem from last week's lesson, solutions to first order equations, as long as everything is continuous, do not intersect. With that information, we could sketch graphs like this. On the bottom part, between 0 and k over 2, it's increasing and concave up. On the middle part, increasing and concave down, and it can't intersect with y is equal to k. We can't have a solution which goes up like this because then it would intersect with y equal to k. So instead, the solutions can get closer and closer to y is equal to k, but they can't touch it. They can't intersect with it. And then finally, in the top part, we found that the solutions must be decreasing and concave up. And again, they can't cross over the y equal to k line, but they can get close to it. Because almost all of the solutions are converging to y equal to k, we say that y equal to k is an asymptotically stable equilibrium solution. Or to say it another way, it's an asymptotically stable critical point. Solutions are diverging away from y equal to 0. So we say that y equal to 0 is an unstable equilibrium point or an unstable critical point. We can understand if a critical point is stable or unstable by looking at the green arrows. If all of the green arrows are pointing towards a critical point or an equilibrium solution, then that critical point or equilibrium solution must be asymptotically stable. If the equilibrium solution is in the middle of domain for y, then we might have 2 green arrows. If it's an endpoint, we might only have 1 green arrow. If all of the green arrows are pointing away from the equilibrium solution, then it must be unstable. And there's one more possibility. We might have an arrow on one side, which is pointing towards the equilibrium solution, but the arrow on the other side is pointing away. Then we would know that the equilibrium solution is called semi-stable. Let's do some examples. Find all of the critical points of dy dt is equal to y multiplied by 1 minus y squared, where we're going to allow the initial point, the initial condition, y0 to be any real number, and classify each as asymptotically stable, unstable, or semi-stable. The first thing we do is we plot the graph of f of y against y. Here, f of y is the function y, 1 minus y squared. And that looks like this. Y on the horizontal axis, y prime, or f of y on the vertical axis. And then we draw our green arrows. When the function is positive, we draw an arrow to the right. When the function is negative, we draw an arrow pointing to the left. We can read off the information that we need from this graph. The critical points, the equilibrium solutions, are where the graph crosses the y-axis. That's -1, 0, and 1. And then we can classify each one as asymptotically stable, unstable, or semi-stable by looking at the green arrows. First of all, -1, 2 arrows pointing towards it. This is asymptotically stable. At 0, 2 arrows pointing away. This is unstable. And at 1, this is asymptotically stable. Another one. Find all of the critical points of dy dt is y minus 2 squared. And again, we're looking at any y between -infinity and infinity. And classify each as asymptotically stable, unstable, or semi-stable. We start with the graph of f of y against y. Where does this graph intersect the y-axis? At 0 and at 2. So these are critical points. Are they asymptotically stable, unstable, or semi-stable? Let's start with y equal to 0. Look at the green arrows. Is that stable, asymptotically stable, unstable, or semi-stable? y equal to 0 is unstable because both green arrows are pointing away from the point. What about y equal to 2? Yes, y equal to 2 is semi-stable. Another example. Consider the autonomous differential equation dy dt equal to y to the power 4 minus 5y cubed plus 6y squared. Part 1. Find all of the critical points of this differential equation. Step 2. Sketch the graph of f of y versus y. Step 3. Determine whether each critical point is asymptotically stable, unstable, or semi-stable. And then step 4, sketch 10 or more different solutions of this differential equation. This is actually an exam question which I asked back in 2013, and back in 2013, students had about 30 minutes to solve this question. So, step 1, find all of the critical points. We need to factorize our function to y squared, y minus 2, y minus 3. And then we can see that this is equal to 0 if y is 0, y is 2, or y is 3. Step 2, sketch the graph of f of y against y. Here it is. We don't need an exact curve, we just need to know where is it positive and where is it negative. And then it's going to be useful for the next step to draw our green arrows on this graph. Just here, the function is positive, so arrow to the right. Next part, the function is positive, arrow to the right. Then the function is negative, so arrow to the left. And then finally, the function is positive, so arrow to the right. There we go. Question 3 was classify each one of the critical points as asymptotically stable, unstable, or semi-stable. Y equal to 0 is semi-stable because one arrow is pointing towards it, one arrow is pointing away. Y equal to 2 is asymptotically stable because both arrows are pointing towards it. Y equal to 3 is unstable because both of the arrows are moving away from it. And then part 4 was sketch some solutions. Now, before I show you a computerized version, let's do a quick scribble. We know we have y equal to 2 and we have y equal to 3. And we have y equal to 0. And I'm just going to copy the green arrows across. First it goes up, then it goes up, and then down, and then up. Now I'm going to be plotting y against t, by the way. And then for the rest of the solutions, we make our guesses. If I start, let's say, point 1, We know that it goes up, so it must curve something like this. If I start to say 2.9, the green arrow says it goes down. So I can draw something like this. If I start at 3.1, it must curve up. If I start at minus 0.1, again, it goes up. I can keep sketching some solutions like this, just making some guesses at what the solutions would look like. Or I could plot the exact solutions using a computer. Let's go back to the example about cats. Now let's suppose we move on to our third model. Now let's suppose we want to model the number of cats in Istanbul with the differential equation dy dt is minus r 1 minus y over ty, where t and r are positive constants. Here's a graph of dy dt against y. The critical points are 0 and t. 0 is stable, t is unstable. With this information, we can sketch some solutions. The vertical axis is now the y-axis, and the horizontal axis is now the t-axis. And I've copied the green arrows from the previous slide. The bottom arrow says we go downwards, so these curves must be going downwards. First decreasing in concave down, and then decreasing in concave up. And the top curves must be increasing in concave up, so curve like this. Depending on the initial condition y0, we either have that y tends to 0 or y tends to infinity. The number t is called a threshold level. If we're below t, then no growth happens. In fact, the number of cats in Istanbul would decrease to 0. There are some populations of species in the world which have this threshold property. If there's not enough individuals, then the number of species decreases and decreases, and the species becomes extinct. This model, again, predicts that the number of cats in Istanbul will increase to infinity as if we're above the threshold level. So we need a more advanced model. Let's move on to model number 4. Now I want to consider dy dt is minus r, 1 minus y over t, 1 minus y over k, y, where r, t, and k are all positive constants, and k is a bigger number than t. Graph of y prime against y looks like this. We can see where the critical points are, and we can see if they're stable or unstable. Y equal to 0 is asymptotically stable, y equal to t is unstable, and y equal to k is asymptotically stable. And then we could sketch graphs of some solutions to this differential equation. Curves are always the same. First concave up, then concave down, or vice versa. First concave down, then concave up. Moving away from t, moving towards k, and moving towards 0. And actually, this is quite a good model. This is a model which has been used by biologists in the past to model certain populations of animals. That's all I want to say about this section. Our second topic for today is exact equations. Last week, we looked at two special types of first-order equations. We looked at linear equations and we looked at separable equations. Now I'm going to show you another special type of equation. Let's suppose we want to solve 2x plus y squared plus 2xy, y prime is equal to 0. This equation is not linear and it's not separable. We need a new technique, a new method to solve equations like this. Now note, if we know a special function called psi, I should say this is the Greek letter psi or psi. If we know that psi is x squared plus xy squared, the x partial derivative of this is 2x plus y squared, and the y partial derivative is 2xy. So our differential equation is the same as d psi dx plus d psi dy dx is equal to 0. Because y of x is a function of x, we also have that d dx of psi is the same thing, d psi dx plus d psi dy dx by the chain rule. So our differential equation is basically just d dx of x squared plus xy squared is equal to 0. And we know how to solve this. Integrate both sides. Integral of the left side is just x squared plus xy squared. Integral of 0 is just a constant. So the key step was finding this function psi. If we know psi, then we can write down the solution. Let's look at a more general equation. Let's look at m of x and y plus n of x and y prime is equal to 0. If we can find this special function psi such that d psi dx is m and d psi dy is equal to n, then equation 3 is called an exact equation. If the equation is exact, then we could do the same method that we did before. Our differential equation is basically just the same as d dx of psi is equal to 0. So the solution to our differential equation is then just psi equal to c. So the idea in this chapter is we're going to find this special function psi, and then we're going to write down that the solution is psi is equal to a constant. How do we find this special function psi? To solve an exact equation, step 1, find the special function psi. Step 2, write psi is equal to a constant. Before I go on, I need notation. Let me just remind you. For ordinary derivatives, we use ordinary d's, or we could use prime notation. For partial derivatives, we use curly d's or subscript notation. F subscript x means the partial derivative of f with respect to x. Now, here's the key theorem. Suppose that all of our functions are nice functions. Suppose mn, my, and nx are all continuous on a rectangle. Then the differential equation m plus ny prime equal to 0 is exact if and only if my is equal to nx. So if my is equal to nx is true, then it's possible to find this special function psi. Let's do some examples. Consider this differential equation. Y cos x plus 2x e to the power y plus sine x plus x squared e to the power y minus 1 y prime is equal to 0. Is this differential equation exact? If the answer is yes, solve it. We need to write down m and n. The first function is called m, and the second function is called n. So m is y cos x plus 2x e to the power y, and n is sine x plus x squared e to the power y minus 1. And then we need to do the partial derivatives. We need the partial derivative with respect to y of m and the partial derivative with respect to x of n. My, we pretend that x is a constant, so ignore x. Derivative of y is 1, so derivative of y cos x is just cos x. Ignore the 2x, differentiate e to the power y to get e to the power y. So 2x e to the power y. And then we're going to differentiate n with respect to x. Derivative of sine x is cos x. Derivative of x squared is 2x. Ignore the e to the power y and ignore the minus 1. You get cos x plus 2x e to the power y. And these are the same. My is equal to nx, so therefore this differential equation is exact. That means we can solve it. That means that it's possible to find a special function xi such that xi x is m and xi y is equal to n. We use these two equations to solve the differential equation. We're going to pick one of these equations. It doesn't matter which one we pick. In this example, I'm going to pick the first one. And I'm going to integrate this. I'm actually going to integrate this with respect to x. And I'm doing that because if we differentiate xi and we integrate it, we just get xi. Integral with respect to x of cos x is sine x, so I get y sine x. Integral of 2x e to the power y with respect to x is x squared e to the power y. Now, when we integrate with just one variable involved, we would have a plus constant on the end. But if we have two variables, and when we do our integration, we have to add on a function of the other variable. Because I'm integrating with respect to x, the function that I add on must be a function of y. And then the next step is to differentiate. Because at first I integrated with respect to x, I'm then going to differentiate with respect to the other variable. I'm going to differentiate with respect to y. Derivative of y sine x with respect to y is just sine x. Derivative of x squared e to the power y is x squared e to the power y. Derivative of h is h prime. So xi y is sine x plus x squared e to the power y plus h prime. But we also started with another equation for xi y. We also started with xi y is sine x plus x squared e to the power y minus 1. And these must be the same. They're almost the same. We have sine x, we have sine x. We have x squared e to the power y, we have x squared e to the power y. We need to have that h prime is minus 1. We need to choose a function h which satisfies h prime is equal to minus 1. We don't need to find every possible h because we're going to be putting the constant in later. We just need to find one function which differentiates to minus 1. So we could take h of y is minus y. But now we know xi. Xi is y sine x plus x squared e to the power y plus h, and h is minus y. So xi is y sine x plus x squared e to the power y minus y. And as soon as we know xi, we know the solution to the differential equation. Because the solution to the differential equation is just xi is equal to c. Okay, let's do another one. Consider y e to the power xy plus e to the power xy, y prime is equal to 0. Is this differential equation exact? If the answer is yes, then solve it. We start with mn, my, and nx. First function is m, second function is n. Differentiate m with respect to y, I get e to the power xy plus xy e to the power xy. Differentiate n with respect to x, I get y e to the power xy. So is this differential equation exact? In other words, I'm asking you, is my the same as nx? And the answer is no. My is not the same as nx. This differential equation is not exact. Exact means that my is equal to nx, but here these are different functions, so the equation is not exact. Another one. Consider 4x cubed y cubed plus 1 over x plus 3x to the power 4y squared plus 1 over y prime is equal to 0. Is this ODE exact? And if the answer is yes, solve it. I'm going to leave this one for you to do. If you re-watch this or if you're reading the lecture notes, pause it or get some scrap paper. Check that this equation is exact. The answer is yes, it is exact. And then solve it and you'll find that the solution is x to the power 4 y cubed plus natural logarithm of the absolute value of x plus natural logarithm of the absolute value of y is equal to c. I'm going to move on. Consider 1 plus 2y plus 3y squared, y prime is equal to 0. Is this differential equation exact? If the answer is yes, solve it. Here, m is the function 1, and y is 0. N is the function 1 plus 2y plus 3y squared. So then nx is equal to 0. Is this equation exact? The answer is yes. My is the same as nx, so this equation is exact. That means there exists a function xi such that xi x is 1 and xi y is 1 plus 2y plus 3y squared. We could start with either one of these. We pick one equation to integrate and then differentiate. It doesn't matter which one of these two equations that we start with. So I'm going to solve this problem twice, once starting with the first equation and then once starting with the second equation. And I'm just writing the bare minimum. This is not a perfect answer. I'm not giving all of the details here. If you write an exam answer like this, you're not going to get full marks. Just writing the bare minimum. I'm starting with the first equation. I'm starting with xi x is 1, and I'm going to integrate it. Integrate with respect to x to get x plus h of y, and then differentiate it with respect to the other variable. Because I integrated with respect to x, I'm going to differentiate with respect to y to get h prime of y. Compare that with the equation at the top. We can see that h prime must be 1 plus 2y plus 3y squared. So then we want the function h to be y plus y squared plus y cubed. As soon as we know h, we can write down xi. Xi is x plus y squared plus y cubed. Let's do the same calculation, but let's start with the second equation. Now I want to start with xi y is 1 plus 2y plus 3y squared. And I want to integrate this equation. This time, because I want to remove the y derivative, I'm going to integrate with respect to y. And when I integrate with respect to y, the constant of integration, or the function of integration, must be a function of x. So I get y plus y squared plus y cubed plus h. If I integrate it with respect to y, the next step is to differentiate with respect to x, always the other variable. So I get xi x is h prime of x. Compare that with the equation at the top. H prime must be 1, so h of x must be x. We end up with the function xi is x plus y squared plus y cubed. Doesn't matter which equation you start with, choose one of them, integrate it and then differentiate it and compare it with the other one. And then as soon as you know the function xi, you know the solution to the differential equation. Because the solution is always xi is equal to a constant. Let's go on to the next one. Consider 3xy plus y squared plus x squared plus xy, y prime is equal to 0. Is this differential equation exact? And if the answer is yes, solve it. Start with mn, my, and nx. My is not the same as nx, so this differential equation is not exact. So usually we would stop here. Our method to solve an exact equation will not work here. But I want to try it anyway. I want to try the method I've been showing you because I want to show why it doesn't work. I want to show you what goes wrong. So some part of the next calculation is going to go wrong. Something will not work properly. Let's see what it is. We're starting by supposing that there exists a function xi such that these are true. We know this is not true. We know that there actually doesn't exist a xi because the equation is not exact. But let's just pretend that there does exist a psi. Take the first equation, integrate it, and then differentiate it, and we get 3 over 2 x squared plus 2xy plus h prime. And that must be the same as the equation that we started with for xy, y. That must be the same as x squared plus xy. So we would need to find a function h which satisfies h prime is minus a half x squared minus xy. And this is where we have a problem. H prime of y needs to be a function only of y. But on the right-hand side, I have both x and y. It's not possible. It's not possible to find a function h of y which solves this. So this is why the method goes wrong. Why did our method fail? Why is it not possible to find h and therefore not possible to find xi? The method failed because my is not the same as nx. So what can we do to solve an equation like this? We can use integrating factors. Do you remember how we solved linear equations? We want to find a special function called an integrating factor that when we multiply our differential equation by the integrating factor, we obtain an exact equation. So let's start with m dx plus n dy is equal to 0. And let's start by supposing that this equation is not exact. We want to multiply it by an integrating factor that we don't know yet. Let's call the integrating factor mu of x and y. So we get mu m dx plus mu n dy is equal to 0. And we know that this equation, equation 5, is exact if and only if the y derivative of the first function is equal to the n derivative is equal to the x derivative of the second function. So we want to have mu m, y partial derivative, is equal to mu n, x partial derivative. And this latter equation, we can use the product rule and rearrange to m mu y minus n mu x plus my minus nx, mu is equal to 0. If we could find a function mu which solves equation 6, then we would have equation 5 is exact, and we know how to solve exact equations. However, equation 6 is a first-order partial differential equations, and partial differential equations are typically not easy to solve. So how can we make this easier? One way to make this easier would be, instead of looking for an integrating factor which is a function of both x and y, we could look for an integrating factor which is only a function of x. Then in the above calculation, we would have that mu y is equal to 0, and equation 6, in fact, becomes this easier equation. Equation 6 would become d mu dx is equal to my minus nx over n mu. Now, we can only solve this if my minus nx over n is a function of x. If this is true, if this is a function only of x, then we can find an integrating factor mu of x. Note that equation 7 is both linear and separable. So you know 2 ways to solve equation 7. If we did the same calculation, but instead of looking at for mu x, we were looking for mu y, we would have a very similar equation. We would obtain d mu dy is nx minus my over m mu. Now, because we're having classroom exams, you're going to be expected to remember equation 7 and equation 8. For example, solve 3xy plus y squared plus x squared plus xy, y prime is equal to 0. We looked at this one before. We know that this equation is not exact. So we're going to try to find an integrating factor. We're going to need m, n, my, and nx. And then we're going to be calculating my minus nx over n and nx minus my over m. The first one, when we substitute in, simplifies to 1 over x. And the second one becomes minus x minus y over y, 3x plus y. The first one's nice and easy. The second one's not easy. So we're going to be using the first one. We're going to be using my minus x over n is equal to 1 over x. Because this is a function only of x, it's going to be possible to find an integrating factor n of x. Because the second one, nx minus my over m, is not a function only of y, it's not possible to find a mu of y. So we want to solve d mu dx is my minus nx over n multiplied by mu. In other words, we want to solve d mu dx is mu over x. This is linear and separable. I'm going to solve this as a separable equation. I'm rearranging it so that all of the mu terms are on the left, all of the x terms are on the right. If I can do this, then I'm allowed to integrate. And after I've integrated, rearranged, I find that mu is equal to cx. We don't need to find every possible integrating factor. We only need to find one which works. So we're free to choose any non-zero constant that we want. I like easy numbers, so I'm going to choose c equal to 1. So I'm going to be using the integrating factor mu of x is equal to x. Great, so let's take the differential equation we started with, which is now in grey, and multiply it by the integrating factor x. We get 3x squared y plus xy squared plus x cubed plus x squared y prime is 0. If we've done this correctly, if we haven't made a mistake, this should now be an exact equation. And yes, my and nx are the same. They're both 3x plus 2xy. We know how to solve exact equations. I'm going to do it I'm going to solve it now, but I'm going to do it quickly because you know how to do this now. We need to find a function psi such that psi x is m, 3x squared y plus xy squared, that's the new m, and psi y is x cubed plus x squared y, the new n. Choose one of these equations, it doesn't matter which one. I'm going to choose the first one again. Integrate the first one with respect to x, and then differentiate with respect to y, and compare it with the other equation that we started with. X cubes on both sides, we can cancel those. X squared, y squared, x squared, y squared. We must have the h prime as 0, so we could choose h is 0. So now we know xi, and as soon as we know xi, we know the solution to the differential equation. One more example. solve y e to the power xy plus 2 over y plus x e to the power xy y prime is equal to 0. This differential equation is not exact. I'll leave this one for you to check. If we calculate my minus nx over n, we get this complicated thing. There's both x and y here. We don't want this. If we calculate nx minus my over m, then we get 2 over y. This is a function only of y. This is what we want. We want to use this one. Because this is a function only of y, we're going to look for an integrating factor mu of y. So we want to solve d mu dy is equal to 2 over y mu. And I'm not going to do this now. I'll leave this for you to solve. Please fill this in, check that my calculation is correct, check that you get the integrating factor y squared. So we take our differential equation that we started with and we multiply it by y squared. This equation should now be exact. I'll leave that for you to check. You know how to solve exact equations, so again, I'm leaving this for you to do. Fill the details in, check everything is correct, and you should find that the solution is y squared e to the power xy is equal to a constant. There's one more topic for today, but before we do that, let's take a 10-minute break. And let's continue. Our final topic for today is using substitutions to change some difficult differential equations into easier differential equations. Remember what you were doing back in Mathematics 1 when you were solving integrals like this? You used a substitution to change a slightly difficult integral into an easy integral. We're going to be doing the same idea in this section. So the idea is if we have a difficult differential equation that we want to solve, we can't do it directly, we're going to do a substitution to change our differential equation into an easier differential equation. We'll solve the easy differential equation, and then we'll do the substitution back again to find the solution that we want. And we're going to use substitutions to solve two types of first-order differential equation: homogeneous equations and Bernoulli equations. First, homogeneous equations. First-order differential equation, dy dx is equal to f of x and y, is called homogeneous if we can write it in the form dy dx is equal to a function of y divided by x. So for example, these differential equations are homogeneous. dy dx is equal to cos y over x, or dy dx is cos x divided by y. dy dx is y over x cubed plus y over x, or dy dx is equal to y over x minus 4 divided by 1 minus y over x. Anytime we can rearrange an equation so that it's a function of y over x, we have a homogeneous equation. And for a homogeneous equation, we use the substitution v of x is equal to y over x. Wherever we have y over x, we're going to replace it with v. Now, that's the same as writing y is equal to x, v of x. And then by the product rule, dy dx is the same as v plus x dv dx. In our differential equations, anytime we see a y over x, we're going to replace it with v. Anytime we see a dy dx, we're going to replace it by v plus x dv dx. So, for example, solve dy dx is y minus 4x divided by x minus y. Note first that if we divide through by x, we get the right-hand side becomes y over x minus 4 divided by 1 minus y over x. This is a homogeneous equation. We're going to replace every y over x by v. So the right-hand side becomes v minus 4 divided by 1 minus v. We're also going to replace dy dx using v plus x dv dx. So we get v plus x dv dx is equal to v minus 4 divided by 1 minus v. If we take this v over to the right-hand side, put everything over the same denominator, we end up with x dv dx is equal to v squared minus 4 divided by 1 minus v. And this is a separable differential equation. You know how to solve separable differential equations, so the rest of this example, or the next part of this example, should be revision for you. What we do is we rearrange it to separate the variables, move all of the v terms to the left and move all of the x terms to the right. Before I integrate, I want to use partial fractions on the left side, and then I integrate both sides to get minus 3 over 4 natural logarithm of the absolute value of v plus 2 minus 1 over 4 natural logarithm of the absolute value of v minus 2 is equal to the natural logarithm of x plus some constant. Rearrange this, and I end up with the equation at the bottom. Absolute value of vx plus 2x all cubed, absolute value of vx minus 2x is equal to some constant c. You should be able to do this. Now that we have an equation for v, there's one more step that we need to do. We need to substitute in again and get an equation for y. Now we're going to replace every vx by y. So here's a vx and here's a vx. Replace these by y and we get our solution. Absolute value of y plus 2x all cubed, absolute value of y minus 2x is equal to a constant. And that's it. That's all we're doing. To solve a homogeneous equation, we do the substitution. V is equal to y over x. And from that, we get dy dx is v plus x dv dx. Always these two equations. Step 2, solve a separable equation. And then step 3, do a substitution again to get a formula for y. I'm going to do one more example. Solve dy dx is x squared plus 3y squared divided by 2xy. First, we rearrange it, divide through by x squared, and we can see that on the right-hand side, we have a function of y divided by x. And then we do our substitutions. Every y of x we replace by v, and dy dx we replace by v plus x dv dx. Rearrange this. We get x dv dx is 1 plus v squared over 2v. This is a separable differential equation. I'll skip ahead. You can check this later. When we solve this separable differential equation, we get 1 plus v squared minus cx is equal to 0. One more step. We need to substitute y back in, replace v by y of x, and rearrange. We get the answer to this problem, x squared plus y squared minus constant x cubed is equal to 0. And that's all it is. Do the substitution, solve a separable equation, and then do a substitution again. The final topic for today is Bernoulli equations. An equation which looks like this. Y prime plus a function p of t y is equal to a function q of t, but now multiplied by y to the power n for some number n. This is a Bernoulli equation. For a Bernoulli equation, the substitution that we always use is v of x is equal to y to the power 1 minus n. Whatever power of n we have in the differential equation, we do the substitution y is equal to the power 1 minus n. Okay, so let's do an example. Solve dy dx minus 3 over 2x y is equal to 2x y to the power minus 1. Here's the n. In this equation, we have n equal to minus 1. So the substitution we want, v is equal to y to the power 1 minus n, is equal to y squared. That's the same as saying that y is equal to v to the power of a half, and therefore dy dx, by the chain rule, dy dv dv dx is a half v to the power minus a half dv dx. We're going to use the orange equation and the green equation to simplify our differential equation. So we take our differential equation, dy dx, I've written in green, minus 3 over 2x, y, I've written in orange, is equal to 2x, y to the power minus 1, I've written in orange. We're going to replace y by v to the power of a half, and we're going to replace dy dx by a half v to the power minus a half dv dx. And what we get is this. A half v to the power minus a half dv dx minus 3 over 2x v to the power of a half is equal to 2x v to the power minus a half. If we multiply this differential equation by 2, v to the power of a half, then it simplifies to dv dx minus 3 over xv is equal to 4x. And this is a linear equation. You know how to solve linear equations. So the next part of this answer should be revision for you. To solve a linear equation, we need an integrating factor. Whatever function we have in front of the v, here it's minus 3 over x, we do e to the power integral of this function, and the integrating factor we want here is x to the power minus 3. So multiply the differential equation by x to the power minus 3. Use the product rule on the left side. d dx of x to the power minus 3v is 4x to the power minus 2. Integrate it, we get a formula for v. And then the final step is to do the substitution again. We're using the substitution v is equal to y squared. So the solution to this differential equation can be written as y squared is equal to minus 4x squared plus a constant x cubed. So let's recap what we're doing here. To solve a Bernoulli equation, we always use the substitution v is equal to y to the power 1 minus n. After we've done that substitution, we solve a linear equation, and then we do the substitution again to get the answer to the equation that we started with. Final example for today's lecture. Solve x dy dx plus 6y is equal to 3x y to the power 4 over 3. Now this time our n is 4 over 3. So the substitution we want to do, v equal to y to the power 1 minus n is the same as y to the power minus a third. That's the same as saying that y is equal to v to the power minus 3. And then when we do the chain rule, dy dx is dy dv dv dx minus 3v to the power minus 4 dv dx. That's what we need to do our substitution. Substitute these in. I'm going deliberately quickly here. You can check this. We get this equation at the top. Divide by 3, multiply by v to the power 4. We get the second one. Divide by minus x, we get this final one. dv dx minus 2 over xv is equal to minus 1. This is a linear equation. We solve this using the integrating factor x to the power minus 2. And I'm going to leave it for you to check that the solution to this linear equation is v is equal to x plus a constant x squared. Now that we know v, we can find y, because v is equal to y to the power minus 1/3. Hence, y is equal to 1 divided by x plus a constant x squared, all cubed. Do the substitution, solve a linear equation, and then do the substitution again to get the answer that we want. And that is the end of this week's lesson, which was a longer than average lesson. Most of my lessons are going to be roughly an hour long, but sometimes they'll be less than an hour, maybe as short as 45 minutes. Sometimes I'm going to be longer than an hour. There's no lesson next week because next Thursday is a half day. So our next lesson is in 2 weeks. And in 2 weeks, we're going to start talking about second and higher order differential equations. Are there any questions?